more importantly, a co-author with me. And he'll be talking today about weak degeneracy of graphs.
Thank you very much, Ryan. Thank you, everybody, for coming. It's a huge pleasure to be here to give this talk. In the recent several months, every time I have an opportunity to give a talk at the board, I just jump on it. So, but I'm somewhat out of practice also. So if it doesn't go well, don't be too angry with me. But I hope that that's going to be all right. So yeah, I'm going to talk about weak degeneracy of graphs, and all of this is joint work with Eugene Lee, who is an undergraduate student at Carnegie Mellon University. I guess he's defending his thesis next week. So yeah, okay. So what is this talk about? Well, I would imagine that a lot of you know what graph degeneracy is. If you don't worry, I will remind you the definition. But the intuition or the motivation for this whole story starts with just trying to understand graph colorings, actually. We want to color graphs, and we want to color them greedily. So really, we're trying to have some kind of coloring procedure in which we have to think as little as possible. And we're trying to understand how well we can do if we only allow us to think very little. So yeah, so let me start with kind of an introduction of graph degeneracy, not this weak degeneracy notion. So what's the setup? We have a graph G, and let me have a function f from the vertices to the natural numbers, which for me is going to, for me natural numbers start with 0. Okay, so what is the meaning of this function? We are imagining that every vertex has a list of colors available to it. Every vertex V has a list, say L of V, of how many colors? At least f of V plus 1. Okay, so it seems that it would be more reasonable to say that it just has at least f of V colors and define things this way. But somehow, just for the definitions to work out correctly, this is the setup. So you have f of V plus, every vertex has f of V plus 1 colors. Maybe I'll available to it. Maybe I'll draw a picture just to illustrate what this can look like. Maybe this is my graph, and the function is something like 2, 1, 1. 1 or something like this, right? So these numbers mean that really this vertex has 3 colors, this vertex has 2 colors, this 2 colors, and this 2 colors. Okay, and we're trying to assign colors to the vertices from their lists in such a way that adjacent vertices get different colors. So the usual list coloring situation. Okay, so, well, let me look at some vertex U. As I said, I'm trying to color the vertices without thinking about anything at all. So I can just grab a vertex and try to color it with an arbitrary color from its list. That's what I'm trying to do. What would happen if I did this? Well, this vertex gets colored, so that's good. But the problem now is with the neighbors of this vertex, because if that color that I used for you happens to be one of the colors available to this vertex, then it's not available anymore, since we cannot color the adjacent vertices with the same color. Which, in terms of this function, we can say that just the value of the function for these guys goes down by 1. So whatever it was before, it reduces by 1. So let me formalize this. Let me say that I have this operation, which I'm going to call delete. So it's an operation of deleting a vertex. So U here is a vertex in the graph, and the output of this operation is a new graph, let's call it G prime, with a new function f prime, where G prime is just G without the vertex U, so we just delete the vertex, and f prime at a vertex V is equal to f of V minus 1 if V is a neighbor of U, and just f of V otherwise. The idea being that once we color U with some color, it doesn't affect the vertices that are not neighbors of U, and the neighbors lose, this is 1, lose 1. Okay, and okay, so this is an operation. The basic operation that we use. Now, well, we want to color the whole graph, so we can apply it to the vertices in some order. What can go wrong? What can go wrong is that vertices can run out of colors eventually, because they lose 1 color. Neighbors of vertices lose a color. one by one. For instance, here, this vertex now, after we remove the vertex here, this only has one color. If we color, and this also only has one color. If we color this vertex now, right, this guy is going to lose one extra color. It has 0 colors available, so we're going to be stuck. And in terms of the function f, this means that the value of the function that was 0 to begin with now becomes -1. So I'm going to say that an application of this operation is, let me use one more color. I'm going to say that the application of this operation is legal if this new function f prime stays non-negative, which just means that every vertex still has at least one color available. And I'm going to say that G is f degenerate if it is possible to remove all the vertices by a sequence of legal applications of this operation delete. So there is some order in which we can remove the vertices one by one, so that the values of the function never go below 0. Okay, that's just the definition. And also, let me say that the one more definition, the kind of the key definition for this, the degeneracy of G, which I'm going to denote by a d of G. This is the smallest natural number d, such that G is d degenerate. Where, what do I mean by d degenerate? D here is just a number. This means that we start with the function being equal to constant function d on all the vertices. Okay. So this discussion should convince you that for any graph G, its chromatic number is at most the degeneracy +1. Right? +1 because we actually, because of all of these +1s everywhere. And actually, because we started with the graph, just every vertex has an arbitrary list of colors. Actually, the same upper bound holds for the list chromatic number. So let me put this in here. Actually, so for those of you who know this, if you don't know what I'm talking about, just ignore this. This next sentence is not going to be relevant. But if you do, then I can insert a bunch of other parameters here. There are various upper bound on the list chromatic number that we can put here that is still bounded by degeneracy +1. For instance, something called the paintability of G, which is the online version of list coloring. Or if you know what DP or correspondence coloring is, you can insert the DP chromatic number in there. So DP, also called correspondence chromatic number, you can insert that in there. That's also bounded by degeneracy +1. Actually, there is a common upper bound for these two things called the DP paintability. You can insert that there as well. That still is bounded by degeneracy +1. Okay. I don't want to define these things because they're not going to be relevant for the rest of the talk. All right, so this is degeneracy. This is great. This well-known upper bound. In fact, it's so well-known. This degeneracy +1 quantity itself has a name. This is called in the literature. Sometimes this is called the coloring number. And this is literally just degeneracy +1. Okay, so, well, okay, how good is this? Well, sometimes it is good. There are lots of graphs for which the chromatic number actually is equal to degeneracy +1. But for some graphs it isn't. And kind of a classic of examples to keep in mind is d-regular graphs for any fixed value d. So graphs where every vertex has exactly d neighbors. A d-regular graph, any d-regular graph, has degeneracy exactly d. This is because no matter in which order you delete the vertices, the last vertex will have lost d neighbors before you get to it. So you have to start with, if the function never goes below 0 at this point, you have to start with value at least d. So the degeneracy is always d, which means that the bound that you get here is d +1. But if d is at least 3, the only d-regular graph with chromatic number d +1, although connected d-regular graph with chromatic number d +1, is a clique on d +1 vertices. That's the only example where that bound would be tight. So we want to be able to improve this a bit, but we still don't want to think too hard. So we want to find a simple way of saving some colors in this greedy procedure that still allows us to do something better than this. And this is where weak degeneracy comes in. So how are we going to save colors? without thinking too much. Well, so let's think about this one step where we're deleting a vertex, and it has a bunch of neighbors. Let's focus on one neighbor, let's call it W. So we're deleting a vertex U with a neighbor W. What if, imagine that f of u happens to be strictly greater than f of w. It just so happens that we have this inequality. Well, in terms of the sizes of the lists of colors, that means that u has strictly more colors available to it than w at this step, right? But this means that there has got to be some color in L of u that does not belong to L of w, right? So there is a color C that's in L of u, but not in L of w. And if we use that, but okay, if we think, so we don't use an arbitrary color for u, we use any color with this property, then what will happen? Well, if we use C for this color C for u, of course, other neighbors of u that are not w could lose this color from the list because we don't know anything, but it's not going to affect w at all, right? And so we save the color for w in this way. So let me formalize it. Formalize it. We have this new operation called del save gf, and now we need two things, u and w. So it's deleting the vertex u while saving a color for w. The output is still a new graph g prime and new function f prime, where g prime is still just g without u, so we do the same thing as before. And f prime now is equal to f of v minus 1 if v is a neighbor of u and it's not w, and f of v otherwise. So we don't change the value for w. But now the conditions for this being illegal operations are a bit more complicated. Put this in a little box. Right. So when is this? When can we actually do this? When is this legal? Yeah. If. Okay. So first, this f prime function still has to be non-negative. That's the same as before. But secondly, this condition has to be fulfilled. Right. So I guess I want to say that f of u has to be strictly greater than f of w. Okay. That's the requirement. If that happens, we can do this. Right, and continue the process in this way. So, okay, so I'm going to say that G is weakly F degenerate if we can remove all vertices via legal applications of, well, I guess I'm allowed to use this operation as well. I don't require saving a color on every step. It's just, so I can use the usual operation delete, but I'm also, if I can, I may save colors in that way. Okay, and the key notion for this talk, weak degeneracy of G, which I'm going to denote by WD of G. This is the same as this. Minimum D such that the graph is weakly degenerate. It's minimum D such that G is weakly degenerate. Okay, that's the definition. And from this previous discussion, it's hopefully you can believe that the chromatic number and even the list chromatic number are in fact, and in fact, so this I'm not going to prove, but you know, you can insert all of these, the paintability and then the dp chromatic number and the dp paintability, whatever that is. All of these things are bounded actually by the weak degeneracy plus 1. Which, of course, is itself bounded by the usual degeneracy. If a graph is degenerate, it's also weakly degenerate. Okay, so we have this chain of inequalities, and now the question that I want to focus for the rest of the talk is, you know, how far can we go here? Is this really a significant improvement, or are there cases in which it's a significant improvement? Okay, are there any questions? Maybe just to make sure that we're on the same page, let's look at a simple example. It's going to be a audience participation sort of thing. So let me try to draw an example of a three regular graph that is not a complete graph on four vertices. I guess I know only one example that I can draw. Okay, here's a three regular graph. And as we discussed, because it's three regular, its degeneracy is 3. But I claim that its weak degeneracy is only 2. Right, so let's see. Yeah. Let's see why. So we start with the value of the function being 2 everywhere, and we want to get rid of all the vertices without ever making the values go below 0. Well, I guess the first step is kind of everything is the same. The only thing we can do is just delete a vertex, and it doesn't matter which one. So say I delete this vertex, all its neighbors lose 1. That's what's happening. So let's do this. 1, 1, 1. Okay, so that's good. Well, what can we do next? Well, now we are in a position to do to acquire some savings, as you can see. For instance, actually, I think in this case it almost doesn't matter what you do. I don't know. Let's try something. Let's try removing this guy, for example, and saving I don't know, one of its neighbors, maybe one of these two. Just why not?
You have to do one of those two.
Right, and I guess it's symmetric anyway. Yeah. We have to do one of those two exactly. Yeah. So this is 2, which is strictly greater than 1. So let's get rid of this. So this goes down to 0. This goes down to 1, but this doesn't change because we saved it. And I think at this point we don't need to even save anything if you're clever about things. I hope. Yeah. Audience participation. what do I do?
Delete the 0 and then delete the upper right too.
Yeah, let's delete the 0 because actually we have to delete 0 before we delete any of its neighbors anyway. Right. So and we will never use it for saving anything. Okay, so let's delete the 0 and then this guy? That was the suggestion? Yeah, okay. So let's in fact we could use this to save things again for its neighbors, but I don't think we would need to.
Maybe you need to down there for the downwards. Maybe you need to save 1.
Oh.
If you don't save 1, you will have 0,
Yeah.
0, and 1.
Yeah, sure. Let's do this. I think there is a way to do it without it, but yeah. Okay, so yeah, let's get rid of this guy and save 1 for this person, which we can. So this becomes 0. This becomes 0. This doesn't change though because we saved it. Now we can safely get rid of this guy without doing anything. We can get rid of this. This becomes a 0. And then we get rid of this again. This becomes a 0. And then we get rid of this. Okay. Perfect. Okay, I've erased everything, so I think we succeeded. Yeah. Okay.
Maybe it will record it.
So I think this hopefully this kind of gives you the intuition for how things work, right? So now let's see what we can prove about this. Unless there are any questions. This is a good time for questions. Okay. So yeah, what can we prove? Well, maybe the first thing you would look at, or I don't know if it is the first thing you would look at, but kind of one of the natural things to look at is what can you say about planar graphs, just because we kind of understand both the coloring, the chromatic numbers of planar graphs and the degeneracy of planar graphs, right? So if I have a planar graph G, then by the 4-color theorem, its chromatic number is at most 4, of course. But actually, this isn't the bound that we should worry about, because as you see, all of these upper bounds that we can get, they're also upper bounds on the list chromatic number and all sorts of other parameters. And actually, so this is the 4-color theorem. But actually, for list chromatic number, there's a theorem of Thomason that says that the list chromatic number of a planar graph is at most 5, and by sharp, and it's sharp by an example of wait. Yeah. So actually, the right bound to strive for is 5 here, because on the other hand, Euler's formula kind of easily shows you that the degeneracy of a planar graph is always at most 5, and that also is sharp. You can see. that's much easier to see that this is sharp, which means that somehow this gives us a bound on the list chromatic number, say, to be at most 5 plus 1, which is 6. And this is, if you teach a graph theory class, this is like an exercise to prove a six-color theorem for planar graphs. It's easy, it follows from degeneracy. And this is the best that you can get from degeneracy, which is one off from what we really want. Well, it turns out that if you switch to weak degeneracy, then you can get the improvement by 1 that you want. So, I guess theorem A. Yeah, I guess, okay, I'm writing this, but every theorem about weak degeneracy I'm going to state is due to us, because we introduced the notion. So for planar graphs, so I guess how can I say this? Planar graphs are weakly for degenerate. Okay. Yeah, so how do you prove this? Well, I will not say too much about this, but if you know how Thomason's theorem is proved, it's proved by induction on the number of vertices on a graph, and the key idea is to prove a stronger statement, as you do when you prove induction. So what we do is we prove this thing by induction number of vertices on the graph with an even stronger statement. So somehow, there's some kind of technical set of conditions that you write down, and then you argue that by induction you can always satisfy this with graphs with a larger number of vertices, and that's somehow how this is proved. Okay, that's as much as I'm going to say about this.
Is it like similar idea?
It is, yeah. It's similar, but more technical. Yeah. It's very, very highly inspired by Thomason's
I
argument.
was wondering if it's like a completely different.
No. Yeah, no. You start with a triangulation and you have vertices on the side. Anyway, yeah. Okay, so this is one illustration how things can be improved. I guess the main point I'm trying to make here is that you get optimal bounds for planar graphs from this very simple way of saving colors. What else can you do? Well, remember I said that regular graphs are kind of problematic, and so let's look at regular graphs. So let me say this is Brooks type theorem. Okay, what can we say for regular graphs? So more generally for graphs of a given maximum degree. If G has maximum degree D, then kind of trivially G is D degenerate. That's kind of obvious. It doesn't matter in which order you remove the vertices, you're going to be fine. Which implies that the chromatic number is at most D plus 1, of course. But when is this bound sharp? As we all know, Brooks' theorem tells us that, okay, for D at least 3, let me ignore the case D equals 2, it's kind of boring. I don't want to write what the whole exceptions are in that case. But for D at least 3, the only connected graphs G of maximum degree D with degeneracy equal to D, sorry, not degeneracy, chromatic number equal to D plus 1. The only such graph is the clique on D plus 1 vertices. That's the unique exception. And of course, every deregular graph is a sharpness example for D degeneracy. So again, it turns out that you can recover this by switching to weak degeneracy from ordinary degeneracy. So the only thing you need to prove, I guess the only tool you need for proving Brooks' theorem is being able to save one color in this funny way. I guess let me write it this way. Say D is at least 3, and G is a graph with maximum degree at most D, and the clique number at most D. Let me phrase it this way. So it doesn't contain a clique on D plus 1 vertices. Then the weak degeneracy is at most D minus 1, rather than at most. See. And hence it's decolorable. Okay. So actually this can be strengthened in some ways. Okay. So here's the strength. Here's one way to strengthen this. Well, let me write it, then I'll say. So let's again D is at least 3, and G is a graph, let's think of the opposite. I have a graph with maximum degree, sorry, I don't know anything about maximum degree, with clique number at most d, so it doesn't contain a d plus 1 clique, and weak degeneracy at least d. So instead of d minus 1, actually, what if it's at least d, right? What can we say about a graph? Well, of course, if it has a clique of size d plus 1, then it would be indeed at least d, right? But what if it doesn't have a clique of size d plus 1? Then the maximum average degree of g, so this is maximum average degree, i.e., this is the maximum over all non-empty subgraphs of their average degree, which I can write twice the number of edges over the number of vertices. Right. So in other words, it's like a local density, the density of the densest subgraph. Think about it this way. So this has to be at least d plus a little bit. Okay, there's some kind of formula for what the little bit is. The main point of this is that this is some quantity that is greater than 0 and only depends on d. So what this says is that if you have a graph that doesn't contain a clique of size d plus 1, and you know that its weak degeneracy is larger than d, then it has to have a subgraph that is substantially, the density of the subgraph is substantially, noticeably greater than this quantity d. Right? Which is, again, not true for ordinary, completely, fails for ordinary degeneracy, because if I have any d-regular graph, the maximum average degree is d, right? And yeah, this degeneracy is also d, right? Regardless of the clique size, right? But in particular, this of course implies this Brooks type theorem, because if your maximum degree is d, then your maximum average degree is also at most d. So this cannot happen, which means that your clique number had to be at least d plus 1. Okay.
Is that sure?
This thing, I don't think so. I don't know. Yeah. I don't know if this is just the quantity that comes up from the from the particular calculation that we have. Maybe or something like that, but I mean, I don't know. I wouldn't be able to tell for sure. Right. This. Okay. If you know Galai's theorem about number of edges in critical graphs, there is something. This quantity is exactly the same as comes up there. If you just think about critical graphs for ordinary coloring, and you ask if I have a critical graph of n vertices, what is the minimum number of edges it can have? And yeah, say it's d plus 1 critical for some value d, right? Then as n goes to infinity, somehow the density of these critical graphs has to be slightly greater than d. For large n, it has to be d plus something, and this is the same something. This is essentially the same bound. Yeah. More questions? So again, I don't want to say too much about the proofs of these things. So I already alluded to the Galai's theorem about critical graphs. The proof kind of is similar to how you might be able to prove that. That's where the maximum average degree comes in. Actually what you do is instead of the graph G, you find a minimal subgraph that has weak degeneracy at least D, and you analyze that, and that essentially has to be dense. That's where this comes from. And maybe I should say that in the middle of analysis you use something. So far I kind of am trying to only talk about the specific value of this weak degeneracy, but if you remember the definition there, I can also ask for graph to be weak f degenerate with respect to any particular function of f. And in particular, what you may be interested is graphs that are weakly f degenerate for where f of a vertex is just equal to the degree of the vertex minus 1, rather than the global maximum degree minus 1. So there is, say in Bliss coloring theory, there is a characterization of graphs that are what is called degree colorable, where every vertex has a list of size equal to its degree. You can essentially the same with some small modifications. Characterization works for graphs that characterize actually graphs that are weakly f degenerate for this function f. And that somehow goes as you prove this first, and then it goes in the ingredient in this calculation. But okay, that's maybe as much as I will say. But, any questions? So, okay. See how we're doing on time? Yeah, excellent. Okay, so this kind of is interesting that some classical results, like these bounds for planar graphs or the Brooks theorem type results, can be recovered just by looking at this weak degeneracy parameter. So you don't actually need to use clever techniques for coloring somehow. You don't need to think about coloring really. You just need to be able to save colors in this funny way. But all of this is upper bound. Okay, let's try to think about lower bounds just to see how far we can actually hope to go, right? What about lower bounds? Well, kind of annoyingly, it turns out that you cannot really go that far. Although you go far enough to get these things. So there is this extremely simple lower bound, what we call the proposition. Let's think about regular graphs because they seem kind of the worst for us. Say I have a deregular graph with n vertices. Then the weak degeneracy is at least, okay, so we know that it actually is at most d and d minus 1 unless there's a clique, right? But it's, so by how much can it be less than d? Well, it's always at least d minus some constant times root n, where n is the number of vertices in the graph. Which, okay, like if you think about it, d of course could be much less than n. But on the other hand, it doesn't have to be much less than that, right? In particular, as a corollary of this, right? If n is just something that's linear in D, which could happen, right? This is how many vertices you need to have to be a deregular graph. Then the weak degeneracy is at least D minus, something like root D. So graphs, smallish graphs, regular graphs, you cannot save more than something like root D total. And actually, we have a conjecture that this assumption is not needed. So here's open problems, right? There's going to be a few open questions. Here's a conjecture that we have that actually for any deregular graph, G, the weak degeneracy should be at least D minus some constant times root D. It really seems to us that the only reason why we can, why there is this requirement that n has to be linear in D is because our proof of this is too silly. It's in fact, let me show you the proof. This is very easy. It's so easy that I'm gonna essentially give you the complete proof here. Here's the proof. Well, suppose that the weak degeneracy is, D minus something, right? And I want to argue that T has to be at least some constant times root n. Well, what does this mean? This means that there is some order in which I can delete the vertices. Let me put them in this order. Right. Okay, so I'm removing the vertices one by one like this. So each time either I just delete the vertex or I delete with the saving, right? Let me look at the last square root n vertices in this ordering. What's the problem with these guys? Well, look at this last vertex. It is preceded by d of its neighbors, right? But we only start with the function being d minus t at this point, so we had to save it at least t times. So it's saved at least t times, right? And similarly, the vertex that's, the penultimate vertex has d minus 1 neighbors at least before it, and so it had to be saved at least t minus 1 times. And this last, etc., right? This last vertex here has to be saved at least something like t minus root n times. Maybe plus or minus 1, let's ignore this. So each of these has to be saved at least t minus root n times. But on the other hand, every vertex can save only one other vertex, right? So the total number of savings is certainly at most n, but it has got to be at least at least root n times t minus root n, right? Right, okay, and from this it follows, something follows, right? So, follows the t is at most, what do we get? 2 root n. Okay, great. Okay, yeah, so you can see why this wouldn't work if n is very large, but we still feel that this probably should be right. Okay. Any questions? All right. So, in view of this type of bound, for the remainder of this talk, I would like to focus on the following question: when can we actually prove an upper bound of this form as well? What are the classes of graphs of deregular or maximum degree D, say, where you can actually prove that the degeneracy is at most D minus some constant times root D, which is kind of the best thing that you can, as a function of D, that you can hope maybe. And we have another conjecture about this, which is also open. and I invite everybody to think about it. There is a conjecture. This is a daring conjecture. We have very little evidence for its truth. I will show you all the evidence that we have, but why not, right? So the conjecture is this: for every integer k, if say the maximum degree of a graph for every k, if the maximum degree of a graph is at most d, and the clique number is at most k, then the weak degeneracy is at most d minus some constant times root d, where the constant can depend on k. Depends. Okay. And I don't care how. So in other words, what I'm saying is that I want to say that for every k, if I look at the class of graphs without a clique of size k plus 1, then they have to satisfy an inequality like this, where maybe the constant factor here somehow gets smaller as k goes to infinity. Does the question make sense? So this is very open. In fact, we cannot even prove it for k equals to 2. So in other words, for k equals to 2, the question is this: is it true that triangle-free graphs of maximum degree d have weak degeneracy at most d minus constant times root d? It seems plausible, but we cannot prove this. But there is something that we can prove, some weaker versions that kind of, maybe inspire us to conjecture that this might be the case. So let me actually state the theorem. Okay, so there are two parts. Okay, two weaker versions of this. So here, this is bound in the clique number, right? We can prove this if this is a bound, instead of being a bound in a clique number, is bound in the chromatic number. So for all k, if the maximum degree of a graph is at most d, and the chromatic number is at most k, then the weak degeneracy is at least, at most d minus some constant times root d, where again the constant depends on k. So, in some senses, maybe this is a little bit silly because we kind of invented this to study colorings, but now we're assuming that the graph can be colored with k colors. But still, this works as some sort of evidence in support of this, because of course, if a graph has chromatic number bounded by k, then this clique number is also bounded by k, right? Let me also point out, this depends on k. In our proof, this depends on k kind of badly. This is something on the order of 1 over k to the k, or something like this. That's the constant factor that we get. So that's really bad. It's another question is, can you do anything better than this? I'll show you a brief sketch of this proof, and you'll see where the k to the k comes from. Okay. Second part. Let's focus on this. So for triangle-free graphs, right? For k equals 2, this says that for triangle-free graphs, such a bound should hold. We cannot prove this, but we can prove it for graphs without triangles and 4 cycles. So if the girth of G is at least 5, which means that there are no triangles and 4 cycles, then the maximum degree is D, then the weak degeneracy is most D minus some constant times. So annoyingly, we couldn't get rid of the assumption about the 4 cycles. Okay. Any questions at this point? While I'm erasing. Okay. So, let me tell you, so in the remaining 10 minutes or something, let me tell you some proof ideas. Depending how time goes, maybe I'll sketch essentially what happens in this part. And these two proofs they rely on similar ideas, but they develop them in kind of completely different directions. And one part of this is that the proofs essentially, both proofs essentially, in an essential way, rely on some probabilistic arguments. All right. So here's a key notion that both proofs use. Let's imagine. Okay, so let's fix the graph G, and let me just assume that it's deregular. throughout, right? And also because I care only about asymptotics, I'm going to assume that D is large. Sufficiently large for everything that I say to make sense. If I have, so here's the definition. I'm putting it in quotes because actually I will not write it precisely. There's going to be some error terms that I don't want to write on the board. So if I have a subset of the vertices of my graph, and some number p between 0 and 1, I'm going to say that the set A prime is a p-regular subset of A if every vertex of my graph, the number of neighbors of this vertex in A prime, this is my notation for this, so degree sub something is number of neighbors in this set, is roughly p times the number of neighbors of V in A. Okay, and this is the part I don't want to explain, so can make this rigorous. Right, so there are some upper lower bounds. This has to be greater than something, less than something. But the point is that it's roughly p times this, right? And this has to be true for every vertex. Now, an observation is, it's called a lemma, also in quotes. Such a thing always exists. So for any A and P can find a p-regular subset. Okay. Yeah. And how to prove this? I'm going to say some words which, for some of you, it will be obvious how to finish the proof, and if not, then just believe me that you can prove this. Just do everything randomly, construct a set A prime by including every vertex with probability p independently, and use the lowest local lemma. Okay. Right. For every vertex with very high probability, you're going to see a p fraction of the neighbors included in the set, and now you use some Chernoff and local lemma. Okay. If this didn't mean anything to you, then don't worry about it. Just believe me that this is true. Okay. So we're going to use this in both proofs. Okay. So let me focus on this first part. So I'm assuming that the chromatic number is at most k. This is my assumption now. Here's what I'm going to do. Let me say that B is a 1 over root D regular subset of the whole vertex set. So which means that every vertex has about root D neighbors in B, because my graph was D regular. So every vertex has roughly root D neighbors in the set. Here's what I'm going to do. Oh, let's say A is the rest. So the vertices minus B. Here's my plan. I'm going to be removing the vertices in A first. So all the vertices not in the special set B. And then, I'm going to somehow deal with them. And then I'm going to remove the vertices in B. Now, because everyone here has, roughly root D neighbors in B, I don't actually need to save these vertices at all. Because, we start with D minus some constant root D at each point, right? Everybody here is preceded by at most D minus roughly root D of its neighbors, so they don't need to be saved, even once. So that's good. That's why I'm putting the vertices in B in the end, right? But these guys here, they're problematic because they have lots of, maybe most of their neighbors are in A, right? So what are we going to do? Or, they're in B but still precede them, right? So we're going to make sure that every single vertex in B is actually saved throughout the process, at least a constant times root D times, and then we'll win. So we want to save each of these vertices at least a constant times root D times. And then these vertices are also going to be happy. How are we going to do this? Here's where the chromatic number assumption becomes relevant. So since the chromatic number of G is at most k, we can partition A into k independent sets. Okay. Now look at this picture again. Everybody in B has, you know, D roughly something like D minus root D neighbors in A by construction, which, you know, is essentially D, right? Certainly linear in D. And now A is partitioned into these K subsets. You know, there's the A1, A2, AK, right? Which means that everybody here has to have at least, you know, a kth fraction of its neighbors in A have to fall into one of these. So let's partition B accordingly. So B is partitioned to the sets B1, BK, so that every vertex W in BI has at least roughly D over K neighbors in AI, right? So for every vertex there is at least one AI that works. We put it in the corresponding BI. And now I'm going to use the vertices in AI to save the vertices in BI. That's my plan. Let me draw some pictures. So the sort of let's zoom in on. Oh, this doesn't work. Thank you.
No guarantees.
Well, it's slightly different. Okay, so we have the B1. Let's zoom in on B1 and A1. I want to draw them this way. Okay, how many neighbors do people have in these sets? Everybody here has, as we decided, by construction, something like D over K neighbors here, whereas everybody here has still something like root D neighbors there, maybe even less. Right? So now it's a simple application of Hall's theorem. We can find for each vertex in B1 a set, let's call it SW, which is a subset of the neighborhood of W intersection with A. So for each W, we have this set of neighbors, such that these sets are disjoint and they're large. So the size is at least something like the ratio of these two numbers, D over K, roughly, over root D, which is, I guess it's something like root D over K. So it's still constant times root D at this point. Okay, so we have these sets. Okay, how can I use this? Well, now, here's what I can do. I can delete the vertices in the set SW. And look, we start with the function that we start with, and all the vertices is constant. So this first vertex, when we delete it, okay, cannot use it to save anything. But once we've deleted it, this vertex W lost a color, right? Nobody in A, though, did lose a color because this A1 is an independent set. Which means that now we can use all of these other vertices to save W. And so we're saving it a constant times root D times, right? And then we repeat it for all of these other vertices. You delete the first, and then you do the saving with the other ones. And then you're satisfied B1, with B1, right? Does it make sense? Okay, we've dealt with B1, but now we need to deal with the rest, right? And what are we going to do there? Well, of course, now we want to just iterate this. Let's look at B2 and A2 and do the same thing. And let me just draw it here. And of course, we can find the same type of structure here. So for everybody here, we also pick a set. And they're all disjoint. But now there is a problem. Here's the problem. As we're deleting these guys and doing the savings, well, vertices in A2 can have neighbors in A1. They can be losing stuff, and maybe they lose way too much. And now they cannot be used to save the corresponding vertices in B2. So how do we fix this? This is where this very tiny constant comes into play. We are modifying the picture. We're saying that we're finding inside of A1 a set D1, which is epsilon1 regular, where epsilon1 is really, really small, but positive, still a positive constant. So let me try to redraw the picture. I'm drawing it very big, but actually it's tiny compared to the whole of A1. Okay, because it's epsilon1 regular, well, everybody here still has less than something like root D neighbors in B1, and the guys in B1 still have at least epsilon 1 over k d neighbors here, which is still linear versus square root, because epsilon is still a small constant. So we can do this whole construction just using the vertices in D1, making sure that these sets SW are in here. Now, we do the same thing with the savings as I described. What happens here? Well, these people could have lost something, but how much? At most, all of their neighbors in the set D1, right? And how many neighbors in D1 do you have? At most, epsilon 1d, right? On the other hand, how many neighbors did you have in B2? At least d over k. So now, after this, sorry, that's not what I wanted to say. I'm getting ahead of myself. Yeah, so okay. Let me erase this. Okay, so these guys lost at most epsilon 1d, right? We want to make sure that these lose more. How do we do this? We find inside of here a set C2, which is epsilon 2 regular, where epsilon 2 is still a small constant, but is much greater than even k times epsilon 1. Okay? And now we just delete all of these without saving anything. What happens? How much do these guys lose at this point? Well, how many neighbors do they have in the set C2? At least epsilon 2 times d over k, which happens to be much, much greater than epsilon 1d because of the choice of epsilon 2. So by doing this, we ensure that these people lose much more and still can be saved by the vertices here. And now this process can be iterated, but as you can see, we're picking up a factor of k each time. So we have to start with the first epsilon 1 being something like 1 over k to the k for this to work. Okay, so I guess I'm out of time, so I will not say much about the proof in the girth 5 case. But it also involves this notion of regular subsets, but it's a bit different. Thank you.
I have a silly question. How big can the gap be between the, let's say, list coloring and this weak degeneracy? Between coloring and list coloring, it's arbitrary. Can you say
yeah. So somehow the examples that illustrate all of these sorts of gaps between different parameters that we have are complete bipartite graphs are good examples. K, D, D. This is a deregular graph, so its degeneracy is D, right? Its chromatic number is 2. Its least chromatic number is something like log D. Its TP chromatic number, if you know what that is something like D over log D. And its weak degeneracy is D minus root D. So all of the numbers are separated by arbitrarily large gaps in this sequence.
So I know you probably don't care, but people seem to like degeneracy because it's easy to compute, right? You can just compute it greedily.
Yeah, I have no idea how hard it is computationally to find this out. If I give you a graph, because the difficulty here is that this is optimized over an arbitrary... how do you compute degeneracy?
Literally just delete min-degree vertices.
Yeah, so this has to do with the fact that for degeneracy there is a nice equivalent definition which says that the graph is de-degenerate even only if every subgraph has every non-empty subgraph has a vertex of degree at most d. This is an equivalent definition, and now you can see, you start with the whole graph. It does have a vertex of degree at most d. If not, then you lose. If he has deleted it, continue. Right, exactly. So I don't know of any equivalent definition of this sort for weak degeneracy. And in general, right, yeah. So now somehow you need to optimize over all the orderings and all the savings, right? Yeah. Like you're saying there exists. I guess it's like clearly in NP of some problem, but I don't. Yeah, I don't know how actually algorithmically hard it is to find out. Yeah.
Any other questions?
Ask one more. So do discharging kind of arguments work for these two? Like that you have this thing, you remove some reducible configuration for list coloring, and then you mess up with it.
I would imagine that they should.
Small number.
In fact, somehow, kind of the proof of, say, this Brooks theorem, the way we write it, can kind of be seen as a baby discharging argument in some sense, because we're saying that unless there is a subgraph of, if you find a subgraph of a certain kind, then you kind of can do the rest like complement the subgraph greedily, and then in the subgraph you do something. So it seems like kind of like a reducible configuration type of argument. But I don't. I mean, I would imagine that you can do more sophisticated things of that sort as well. But that remains to be explored.